morning session themed on star formation and feedback. We also add a little bit dark matter theme to this particular section of the morning session. Next talk is by Zhao Zhang. He's going to telling us about probing the cosmic baryon distribution and AGN impact with FRBs.
And just a quick reminder, please, on the program website, scroll to the bottom and remember there's a link there to upload your slides. I am putting those into the program as I get them. And for poster presenters, you can also upload your posters there. I'll also link them in the program so everybody can peruse those in more detail.
And the speakers who want to be filmed can stand here, right? Around this corner. Yeah.
Testing. Can you hear me? Okay, good. Okay, hello everyone. I'm Zhao Zhang from the University of Osaka. I'm a third-year PhD student. My supervisor is Ken Nagamine. And this is actually the first time I came US, attending this wonderful workshop in Santa Cruz. And I'm actually, so my talk title will be probing the cosmic baryon distribution and AGN feedback impact with FRBs in CROCODILE simulation. Okay, so there are about the baryon distribution probes. There have been actually several useful tools like SC effect, X-ray, or Lama forest. But today we're gonna talk about another probes called FRB, fast radio burst. So here I show why the FRB can help do cosmology. So because the fast radio burst, the photons in different frequencies have a time delay when FRB cross cosmic structures, and we can quantify the time delay by a value called dispersion measure, and we use this dispersion measure also equals to the electron number density. So this diagram shows how the FRB cross the universe, and the FRB is generated from the host galaxies, and then passing through the intergalactic medium and several foreground halos. Before arriving on Earth, it will cross the Milky Way also. So each component of the cosmic structures will do contribution to this DM. But the main fraction will be the DM AGM. So if we assume the baryons are uniformly distributed in the intergalactic medium, we will have a linear relationship between DM and redshift, which known as DMZ relation and also Marquardt relation. So people observationally are widely using this equation to constrain a cosmological parameter called FIGM. This is a mass fraction of the baryons in the AGM, but we should emphasize that in our simulation results, we found that this FIGM actually being strongly polluted by the foreground halos. So we use this F diffuse new term to replace FIGM. This is the sum up of the halos and AGM combinations. And in our work, we use zoom-in simulation for the host galaxy DM analysis and use the large-scale simulation for AGM and foreground halos. And we also did some AGN feedback effect analysis in this part. And here in this slide, we show the previous observational work on constraining the FIGM. So they can constrain to be over 80%, but we should also note here their FIGM should be compared with our F diffuse in this work. And here we emphasize the importance of the foreground galaxy survey of the FRB. So there are 4 FRBs Senha used in 2023 to probe to do the foreground galaxy survey, and they have the DM axis deviate from the Marquardt relation. And he do the zoom-in field for these 4 FRB satellites, and he found the foreground galaxies marked as blue circles. Those blue circles, the depth of the color is the contribution of the DM. So we can see the bottom 2 panels are well explained by foreground data. when the FRB passes through the foreground galaxies, the DM surge. So that means the foreground data can help us to make the FRB cosmology more accurate. But we also can see the bottom two are not well explained by the foreground data. We guess the reason we guess there are two reasons. One, maybe there are some dwarf galaxies we didn't discover, so we need a large aperture telescope like LSST. And the other reason probably be the excess of the DM host. And this reason makes our motivation to do research on the host galaxies. But the FRB can be located in any kind of galaxies. They can be located in the dwarf, the Milky Way-like galaxy, or the galaxy cluster even. And they also can be located in the star-forming region or the spiral arms of these galaxies. So each location, the different location will make the DM vary significantly. And now let's see what we have done using our hydro simulation. Okay, so our data set is from the CROCODILE simulation, which is based on the Gadget 3 and 4 Osaka SPH code. And the left two tables are showing the initial condition and some initial sightings for our simulation. And the right hand 6 figures are our box wrong, simulation box. There are 25 fiducial wrong and 500 no black hole wrong, and 100 with and without agent, 50 with and without agent. So we shoot satellites in this box and we construct the light cone data using them. We shoot 10,000 satellite numbers, and we can get our DMZ relation based on the simulation work. Then we found they follow the log normal distribution, and the redshift 1 DM diffuse for fiducial is 936 parsec per cubic centimeters, and for no black hole it's 927. This is consistent with the observation. And then we can use this Macquarie equation to constrain the F diffuse. And for fiducial, our F diffuse is around 86.5%, and for no black hole, it's 85.6. So they are also comparable to the observation, but we found that between the fiducial and no black hole, there are small differences. What's the reason? We guess it's due to the efficiency of the aging feedback. So because our CROCODILE simulation now lack of the aging jet feedback, and there is no radiative transfer, which can help ionize the gas. Okay, so here we show how we make the foreground galaxies analysis. We select the halos in each mass range from 10 to 10.5 to 10 to 15.5 solar miles. It is from the dwarf to the galaxy cluster, and we retrieve the data within 2 field radius and shoot satellites from the center to outside, and we calculate the DM versus the impact parameter B. And the results are shown in the right hand. And here we found that in the large mass range, there are the fiducial wrong center DM is strongly surprised by the aging feedback. And we found the large difference happens to 10 to 12.5 to 10 to 13.5. So we think this is a strong CGM and IGM baryon redistribution mass range. But due to the time limitation, I will not say too much about this aging feedback analysis. If you are interested, you can check my archive paper, the appendix part, and also talk with me in a coffee break. Coffee break is over. And okay, so we also compared our results with some other work, like Medlock 2023. She used Camel's simulation for the mass range 10 to 11 to 10 to 13 solar miles, and they are they are consistent with our results in the similar mass range. And also we compared our results with the observation, like KGA's work. He found a FRB crossing 2 galaxy cluster, whose mass are over 10 to 14, and they are also aligned with our results. And here we show the corners observation about the host galaxy of the cluster of FRB. So we found that the first one in the blue, it's a little bit higher than our density profile, but the yellow one is in our mass range constraint. Okay, so with the sufficient of the foreground galaxies knowledge, we can use them to extract the intrinsic FIGM by removing the CGM gas. But the CGM is somewhat unclear definition. So we need to do some definition of the CGM. We use 1 virial radius, 2 virial radius, and 3 virial radius. Also the OF radius. And after we removing the gas, we can extract the intrinsic FIGM, showing the panel A in the top. And they have from the top to bottom, it's 1, 2, 3 virial radius after removing the gas, and the FIGM is actually converging to 1 in the higher redshift because there is no halo in higher redshift. And we also in the panel B we show the F diffuse of the FRB observables, which constrained by the Marquardt relation, and the black one is the fiducial one, and the red one is no black hole. And we found that the F diffuse has a larger slope compared with the FIGM. This is because when the redshift increasing, more foreground galaxy will cross the FRB sidelines, which makes this slope become sharper. And so, but we found that this F diffuse is in between 1 virial radius and 2 virial radius. So the CGM can be defined in this 2 radius. And we use some models to fit this trend. And we found that FIGM is following the DPL EXP, and the F diffuse are following the CPL EXP. So please take a note of this because we're going to use it. And the DM diffuse here, we are using the simulation accurately extract the intrinsic FIGM. But could we do this for the real observation? Yes, we can, but only if we have enough strong resolutions and sensitivity of the telescope. So, but in practice, due to limitations, we need to do some semi-analytical approximation for those observable we can currently use. So let's go further into the F diffuse. And like this F diffuse is actually outside the integration of the redshift. But is that true for the real F diffuse? Because when FRB cross cosmos, it's not just carried the local environment information, but it has memory of the cosmological historical evolution. So we need to use the integration of the redshift of the FIGM and F fields, which can be shown in the red panels. They are evolved. And except for this integration, we know the single FRB sideline means nothing because it is so stochastic. So we need numerous FRB sidelines to calculate the statistic average. Then we can make our observation meaningful. So we make this F diffuse integration and statistical average. And remember, we use this equation to fit the F diffuse. So this can be analytical. Then the equation 3 is analytical solution. But and if we consider the FIGM and F intersecting halo in the temporal evolution of the redshift, we can get this. We can get them within the integral. Then we got the equation 4, but the intersecting halo is kind of related to the cross probability of the FRBs. So we need to do some average also. Here the n is the halo mass function. For example, we can use the Press-Chater 74 to do the semi-analytical solution, and this sigma g is surface density of the halo. We can use a DMB profile shown in the last slides. Also, we can use theoretical model like NFW and modified NFW. And in principle, the equation 3 and 4 are equivalent. So if we do the differentiate for both sides, then we set them equal. We can get this relation in the red box. So what's important here is the FIGM is actually the intrinsic FIGM. Our cosmology really cares. But the right-hand set terms are all observables and equations, semi-analytical equations. So we can construct this framework to reconstruct this FIGM by some semi-analytical annihilation without strong resolution telescopes. And here we show our results, and we do some, I think I don't have time, so I will skip this. We do some zoom-in analysis for host galaxies, and we got the median DM for each of the galaxies for dwarf galaxy and Milky Way-like galaxy and the galaxy cluster. They are 460 and 1,600. And this is something new. I found this last night. There is a higher redshift FRB is localized in a dwarf galaxy at redshift 2. So that means if this localization is accurate, then we can look forward to the more higher redshift FRB cosmology. Okay, I will leave my summary here. Thank you.
Okay, thank you. Very interesting, but we only have time for very quick question while Jonathan is setting up.
Thank you. This is interesting work. I was just wondering, in these simulations, if these are just single FRBs or if they're repeating, and if you see like any difference in like the dispersion measure of a repeating FRB after like multiple repeating events, and if that like fraction of single versus repeating FRBs changes with redshift.
So you mean the dispersion, the differences between the repeating and non-repeating FRBs? Yeah. So because the repeating FRBs we generally can localized, so we sometimes can better constrain their DM by removing the host galaxy contribution. But non-repeating, we have nothing about their host galaxy. We cannot actually localize them, so we don't know where are they, and we can only use the DM for constrain their redshift.
Okay, let's thank our speaker again.